In this presentation, Syed and myself will examine the potential for short-haul aircraft powered by cryogenically compressed gaseous hydrogen. This will mainly be done using a comparison to traditional Jet A1 powered aircraft through the PSFC, or power-specific fuel consumption. From the PSFC, fuel mass burn and tank volume will be determined. Further, modifications required for a conversion from Jet A1 to gaseous hydrogen are detailed.
So this presentation will include our inputs as well as our assumptions for this task. We will also be investigating the effect of the changes in Mach number as well as the turbine temperature on the PSFC and illustrating that through our graphs. And we will be doing the same with the compressor pressure ratio as well as the compressor adiabatic efficiency and the effect of the changes of those values on the PSFC. And then we'll be moving on to calculating the fuel mass burn as well as displaying the minimum fuel tank volume required to accommodate the suitable and ideal fuel. And lastly, we will discuss the modifications necessary to be able to store that fuel safely within the aircraft. So for our inputs, we've gone with the cruise Mach number of 0.6 as well as a cruise altitude of 30,000 feet or about 9,000 meters, where the ambient temperature is expected to be close to 230 Kelvin as well as an ambient pressure of about 30 kilopascals. For this task, we've gone with modeling it after the Dash 8 Q400, which is one of de Havilland's aircrafts, and this will be running on a Pratt and Whitney model PW150A. As can be seen from these graphs, there isn't a whole lot of difference when we do increase the Mach number on the PSFC, very consistent values moving from 0.2 to 0.8 Mach number, so no real changes in there. However, there is a slight decrease in the power specific fuel consumption when the turbine entry temperature is increased from about 1000 Kelvin to 2000 Kelvin, and hydrogen seems to be the one with the lowest power specific fuel consumption here. As can be seen, there is a trend of lowering of the PSFC with an increase in the compressor adiabatic efficiency, and this is most pronounced with methanol, where there's a huge decrease in the PSFC from about 50% efficiency to about a 70% efficiency. And moving on to the compressor pressure ratio, again we can see a slight increase in the PSFC with a higher ratio, and it is most pronounced with, once again, methanol, with it increasing from a 0.14 to a 0.18 as the pressure ratio is quadrupled from about 20 to about 80. As can be seen here, we have taken the range to be 750 kilometers. This is keeping in mind the ideal 500 kilometer range, and we've had to add the range that would come into effect because of the reserve fuel requirements by the local aviation regulation authorities, and so that has added another 250 kilometers to that initial range. And as can be seen, the fuel density, fuel tank temperature, and fuel tank pressures have been taken from credible sources and put into this table. And then the final tank volume was calculated. And as can be seen, the Jet A1 requires the least amount of volume with about 1.69 meter cube of space, while hydrogen takes the most amount with about 6.75 meter cubes of space.
There are a number of issues when using cryogenically compressed gaseous hydrogen as fuel, the main of which is storage. BMW have studied the methods of storing different types of hydrogen and propose a cryogenic pressure vessel seen here. However, as hydrogen is 10 times less dense than Jet A1, fuel tanks need to be much larger to accommodate a similar distance's worth of fuel. This is why short-haul aircraft are the best candidates for conversion, as longer, long-haul aircraft would need extensive modifications to their design to accommodate the larger tanks, potentially relocation from the wings to the fuselage. Further, all components between the tanks and the engines, such as fuel pumps, lines and seals, would need to be replaced with parts that can sustain usage with fuel at such low operating temperatures. Additionally, these components need to be as airtight as possible, as hydrogen gas is a relatively small molecule compared to that of jet A1. The fuel-to-air ratio used in these engines needs to be modified, as hydrogen has a much higher flammability potential and may require more or less air to ensure optimum efficiency. Engine part replacements also need to be performed to allow this low temperature use. This includes the nozzles, piping and internal shielding.